Okay, let's continue on the write operation. For the write operation, we need to prepare the data that you want to write into the memory array first from the outside. For example, here if you want to write 1 to the N1 and 0 to the N2, we need to prepare those two data from the outside. That means bit 9 needs to be VDD, bit above needs to be 0. And we assume that the data you stored here, N1 is 0, N2 is 1. That means we are going to flip the data doing the write operation. So we prepare those two data from the bit and bit bar, and then we turn on the word line again. We turn on the word line. So then what will happen here is that if you look at the right hand side, so here this is 0, and then this is VDD, and then you store 1 here, this is VDD. So this transistor is PG2 is on. You have current flow through the PG2. This current must come from the power supply VDD, so you have this green arrow. So this one is going to discharge this N2 node. Initially is VDD, and then later this VDD will decrease. Okay, this VDD will decrease. Similarly, to the left-hand side, you have the green arrow of current. This is the same as the read condition, right? To the left-hand side, this is a read condition, the same as the read condition. So this is read, and this is the write. For the write, you see that this is the same as the read. So that means you're going to have this green arrow for the current. That means N1 will increase a little bit, but N1 will not increase too much because in the read operation, by design, you don't increase it too much. Okay. So that means N1, the 0 to 1 transition will not happen. So what needs to be happen first is that this N2, 1 to 0 transition needs to happen first. What does that mean? That means if you look at the N2 node, okay. Oops. So if the N2 nodes, where's my, oops, sorry. So, okay. So if N2 nodes change from VDD to 0, if you have that, if this change to 0 already, you look at the left-hand side. So this, why is this supposed to change? Okay. So this 0 actually controls the gate of the PU1. So the PMOS will be turned on. So you have additional current here. This is additional current to charge the N1 node. So N1 node will keep increasing further. So the N1 will eventually change from 0 to 1, eventually. But at the very beginning, this N1 will increase a little bit to that V prime, as we discussed earlier. It will not increase anymore until this N2 becomes 0, and then you turn on this PU1. You have additional current to charge, so this N1 will keep increasing, eventually to the 1. So that is the process of the write operation. So what matters is the right-hand side here. You want this N2 to be close to 0 because you want to flip it. You want to change it from 1 to 0. So you need to satisfy some condition as well. So here for this PU2 and PG2, you need to satisfy some condition because here this N2 node initially is 1 and now you want to make it 0. You have 1 to 0 transition. So if you use a resistor as the approximation, you will have similar voltage divider here. So here you have PU2 and PG2. So you want this N2 node close to 0. So here from the voltage divider, you know, you want PG2. If you think of resistance of PG2, to be small than the resistance of the PU2. So you can make N2 close to 0. And how do you do that? Then you want the conductance of Pg2 larger than the conductance of Pu2. And you know conductance, as we discussed before, is mu CoX W over L. But here you notice that Pg, the the pass gate is NMOS, and Pu is PMOS. And you know mu N is larger than mu P. So this one you see that even they have the same W over L, because mu N is larger than mu P, so you can satisfy this condition. So we define this gamma ratio as the ratio of the W over L. So even they are at 1, this should be actually, let's say, less or equal to 1. So even they are the same, okay, even they are the same, because the NMOS mobility is larger than the PMOS. So you can still make the pass gate. So here we want the pass gate to be strong and the pull up to be weak. But even they are the same W over L, because NMOS naturally will be stronger because mobility is higher. So you can satisfy this condition. Or if you look at the timing diagram, you will see that you prepare the bit line to be 1, bit line bar to be 0, and once you turn on the word line, so the N2 node will decaying here, will drop, and then N1 will increase. Once N2 is below some value, then N1 will keep increasing. So eventually you flip the state. This is how you write the new data into the SRAM cell. You change the state. So got another question. Why is the left-hand side bit line set at VDD? Left-hand side bit line set at VDD. Because we want to threaten the new data in. This is our assumption. So here, the old data is 0 to the N1, and now we want to change the data to be 1. So we set the bit line to be 1. Of course, if the new data is 0, then you can provide 0 here, then nothing will happen, because you don't change the data. Here we consider the case where you need to change the data. Okay, so this is the right operation. And let's have a summary here. So read, we need to care about this 0 to 1 disturbance, because we don't want that vprime to increase too much. But for the write, we do want to flip. So we want to have the N2 to have this 1 to 0 transition first. As you can see that the read and write always conflict with each other. This is by nature, right? Read, you want to keep the data even after you read it. But write, you want to change the data. So you have a conflict there. And to make this SRAM work properly, we need to satisfy this condition. For read, large beta ratio, or in other words, strong P pull down, weak pass gate. Or for the write, the weak pull up, strong pass gate. This is what I just described. So in practice, you can have this W over L ratio. This is the W over L ratio. Doesn't work. Oh, doesn't work, my pen. Anyway, so this typical ratio is PD over PG over PU is a W over L ratio. That means W over L ratio for PD will be 2, PG will be 1, PU will be 1. So you can satisfy the condition as we listed here. Even the PG and PU have the same W over L ratio, because the PG is NMOS, PU is PMOS. So you can still make the PG stronger than the PU. All right, so that's for the SRAM lecture. I know it's a little bit complicated. So I encourage you to review the lecture video after class and also read the reference chapter to understand how it works. Any other questions before we stop here?